Recording is starting. Please continue.
All right. Well, thanks very much for having me here today. My name is Jeremy Druin, and I'm a pen tester for a large company in Louisville, and also own Ellipsis Information Security and do pen testing through that company as well. And a couple of projects I've worked on is Matilda, originally started by Adrian Crenshaw. Actually, still have Matilda 1 up on the site for download, and then spun off into a second project, Matilda 2, that is available as well for learning about web application vulnerabilities. So today I was going to talk a little bit about a pen test I was on where ran into some source code that was of interest. We were able to get a hold of the source code of an application, and we wanted to escalate privileges. And it turns out that there were some scripts that were running that had an administrative username and password inside the script, and the script would run every so often and do these administrative type things. And so we weren't so much interested in the source code per se, but we did want to get that admin username and password so we could log in as administrator. But the script had been encrypted. And after studying the way that the file looked, it became more apparent over time that it was a homemade encryption. And eventually we were able to finagle our way into breaking the encryption and getting the username and password out. And so I'm going to use that use case as an example today in a demo of how we worked our way through this problem and figured it out. And go ahead and get to the punchline now in case I forget at the end. But the idea being that anytime that you're going to use encryption, you want to use a good, vetted, modern, approved cipher that's a standard cipher whose security is only based on the key and is not based on, any kind of knowledge about the system. The idea being that if homemade encryption had not been used in this case, we probably wouldn't have been able to get the password the way we did. Not to say we wouldn't have got the password eventually anyway, but we certainly would have had to have used different tactics, maybe phishing or some other tactics, convincing someone to give us the password. It would have gone certainly a different way though. So to start with, the idea of a cipher is to take some plain text and pass that plain text through this algorithm. The algorithm uses a key to obscure this plain text and the ciphertext so that you can't understand it. It makes no sense anymore. It doesn't have any context anymore. And we're all pretty familiar with the idea of encrypting something. But a couple of basic ideas that'll help us a little bit is this idea of substitution and transposition. And most ciphers have a tendency to use one or the other of these or combine these two ideas together into a cipher. So with substitution, we're going to take the plain text and swap it out for something else entirely. So it won't be the plain text anymore. Maybe the letter A gets substituted for the letter X, or maybe the letter B gets substituted for the number 14. But the plain text is actually gone and has been replaced by something else. With transposition, we're not actually going to change any of the plain text at all, but we are going to shuffle it around a bit. So it won't be in the same order that it was in before. It's kind of like shuffling cards. You don't actually add more kings to the deck or change the heart into a shovel. You just simply change the order of the deck when you shuffle the cards. And that's the idea behind transposition. So we're going to look at two basic types of ciphers. There's, not surprisingly, substitution and transposition ciphers. And the substitution ciphers, there's a lot of different types, and one of them will be of particular interest today. To start with, we have a simple substitution cipher. Depending on how the key is set up, sometimes these are called Caesar ciphers with a key of 3, or ROT13 with a key of 13. But the idea is that you have a number that is essentially the key, and you're going to shift the letters that many positions. And so if we used a Caesar cipher, for example, the letter A would be shifted from A to B, C, and D, because D is 3 positions away from the letter A. ROT13 is what we call an involutory key, at least over the English alphabet that has 26 letters, because if you run rot13 twice, you'll get back what you started, since 13 done twice is 26. In other words, you circle all the way back around to the letter you started with. The next best cipher, I suppose you might say, working off of the shift cipher, is the polyalphabetic cipher. And the idea here is we're still going to shift the letter some amount, but each letter gets its own shift. So the first letter gets shifted by the key for that column, and the second letter gets shifted by the amount for that column. And in a good password, those would be different than one another. So let's take the key 1, 2, 3, 4, 5. We would shift the first letter 1 spot, the second letter 2 spots, the third letter 3 spots, and so on. When we got to the sixth letter, we start back over and we'll shift the sixth letter 1 spot again. And on the example here, we can see that the word aardvark starts with 2 A's, but you'll notice that in the ciphertext, it came out using the eye chart on the right to be BC, because there was 2 different keys for the one for the first letter, one for the second letter, one for the third letter, and so on and so forth. The polygram substitution cipher is a lot more like what the modern block ciphers use. The standard ciphers we would use today, like DES and AES, tend to behave this way. And what's going on here is you're taking entire blocks of plain text and you're swapping out the entire block for a whole new block of ciphertext. Makes it a whole lot harder to do the cryptanalysis. And in fact, DS and AES both have this idea of substituting entire blocks after doing some what they call mixing, which is to take the key and mix the plain text up before you go in and do the substitution later in the S box. There's actually a cipher that's unbreakable, and it can even be a shift cipher, or it can be one of these polyalphabetic ciphers. And the idea behind a one-time pad is that the key is at least as long as the plain text itself, hopefully a lot longer. In the book you see here, this is a picture of a book supposedly used during the Cold War, where you would take your message and you would start at the very beginning of the book and read the very first key in the book and use that as the key to encrypt the first letter in your plain text. You would use the second letter in the book for your second letter in your plain text, and so on and so forth. And the book is supposed to be very long, so you can encrypt your entire message and not even use up the entire book. And this kind of a cryptography, even though it's simple, is actually provably unbreakable. The person who figured out the idea suspected it might be unbreakable. Then about 20 years later, a mathematician came behind and proved that it actually was unbreakable. The reason being is that the ciphertext could represent any plain text. Any plain text was just as right of an answer as any other. The only way you could know which one was correct is if you had the original key. It turns out this unbreakable cipher actually was broken, and the Americans figured out that some of their adversaries, Russians, were using the books over and over again because they weren't getting a fresh supply of new cipher key books in these one-time pads. And so when they used the key repeatedly, they broke the cardinal rule of the one-time pad, which is never reuse the one-time pad. And because they were able to do comparisons, they were able to end up breaking some of the codes that way. But that tends to always be the problem with cryptography, at least in the modern age. It's not so much the cryptography that's weak, it's the people using it make mistakes. In the transposition cipher, this is one of those permutation ciphers where basically you're just taking the letters and moving them around. If you notice in the example, we still have the numbers 1 through 9 like we did in the plain text at the top, but you'll see the ciphertext in the second row, the numbers are just all scrambled, even though they're all still present. So is there any questions so far about basic cipher primitives and ways of doing basic encryption? All right, well, to help with understanding how some of this works, I created a new project and I've put it out on GitHub, and it's totally free, so feel free to download it and take credit for it and put your name on it and everything. The idea is that I wanted to implement a lot of the classical ciphers, shift cipher, the Visionaire, which is polyalphabetic, Hill cipher, which is one of those block ciphers we talked about, a substitution cipher or permutation cipher to do the transposition. And also some utilities that would help you be able to do the math that's often associated with breaking these kinds of ciphers and go ahead and automate that process. So for example, we have the hilarity, which implements the Hill cipher, and then we have maitre-d, which does a lot of matrix math to do things like transpositions and adjuncts and stuff that you need to be able to end up trying to figure out if keys are involutory, if you can break them, and so forth. We have the Shifty and Affinity implement two kinds of shift ciphers, the shift and affine cipher. And then Visionary is the one we're going to use today, and it implements the Visionaire cipher, one of the polyalphabetics. And the script that I was talking about early on, that was a polyalphabetic. It was a type of Visionaire cipher that the person had changed just a little bit, but conceptually the idea is going to be exactly the same. So I figure the way to learn this the best is let's do the encryption wrong. We'll use these classical ciphers in a not so secure way, and then let's work through breaking that cipher. And I have substituted a new file for the original one, so there's nothing that's being disclosed here that's secret. But the idea of actually breaking things on purpose, I think, is a useful way to learn a lot of concepts in information security, and especially if you're doing programming. Anytime that I'm helping folks with learning programming, I like to try to do syntactical mistakes on purpose in order to cause the error to occur. That way, down the road, when you make that same mistake again, you'll actually have a chance of remembering, oh, that error means that I probably did this kind of thing wrong. And so we're going to sort of do that same thing with Visionaire. Visionaire also makes a good cipher to study because it's actually not very easy to break. It's fairly difficult if you're new to doing any kind of cryptanalysis. But on the other hand, we can do it. It'll take about 20 minutes, but we can actually break the Visionaire cipher even if we don't know what the password is. It just takes a bit of analysis and putting some tools together. And that's another reason I like to use it as an example is it does let us use a couple different techniques. We're not just going to do one simple thing and be done with the problem. So the setup is we're going to take a picture, JPEG to be specific, and we're going to encrypt that JPEG and then go about the business of trying to figure out what the password is. So of course, if you're going to do this in a classroom environment, one of the best ways to do it would be to partner up, have someone encrypt the file for you with a secret password, and then you all trade and try to break each other's files. And don't worry about copying the code here that I used to do the encryption on the slide. On the GitHub site is the typical readme.md file you normally see associated with GitHub projects, and all of the commands are already there online for you. So we've encrypted this file and come up with encrypted funnycat1.jpg that eventually we're going to attack. So the strategy is going to be to talk about a couple of statistics that are going to help us. We don't really know which ones. We're just going to kind of throw the kitchen sink at it and see what pops out. We also need to talk a little bit about traffic analysis because there's going to be this question that's going to come up of how do you know what kind of file it is you're trying to decrypt? Also, we're going to look at what JPEGs normally look like, look at how Visionaire changes JPEGs. Then we'll have to go about the business of figuring out what the key length is. You'll see why later. And finally, we'll try to recover the key bytes. So as far as statistics goes, today we're going to use just the plain stuff, the mean, median, mode, standard deviation. Entropy can be helpful to help understand files. Like, for example, entropy is real useful if somebody changes a file extension on you from TXT to JPEG. You know, the entropy would give that sort of thing away right away. And we're also going to need a little bit of probability and something called the index of coincidence. That's going to be super helpful pretty soon. All right, so before we get rolling, any questions up to this point? All right, so first let's talk about traffic analysis because we're going to have the same problem in this type of pen testing as we are in all kinds of pen testing. We need to learn about the adversary, a lot about the adversary. The success of the pen test is largely going to hinge on this step. So you have tools that are specifically designed just for this step. In general, we talk about tools like ReconNG, or we talk about Shodan, or other tools like that, where we're doing this sort of passive analysis, this reconnaissance, where we're trying to learn as much about the target as we can. And doing cryptanalysis is no different. You need to learn as much about what it is you're trying to decrypt and how it was decrypted. And so let me repeat that again, because those 2 points are really important. You really need to know what kind of data it is you're trying to decrypt, and you need to know as best as possible what kind of cipher was used to do the encryption. So those are 2 really key points. And traffic analysis can help you with that. You look at who's talking to who and what were they talking about. Did somebody say in a text message, I sent you that picture? You know, that would be a big clue right there. Were they emailing back and forth about how one of them needed a spreadsheet from the other one? Tools like Wireshark and TCP dump and other kinds of traffic capture tools can help you get that kind of information. You may not necessarily be able to read what it is they're sending back and forth, but just what they're saying can give you clues into what's going on in the situation. So now we'll look at what the JPEG files so-called look like normally. What kind of byte structure do they have? What do they typically look like? Not encrypted at all, just what does a normal JPEG picture look like? So one of the ways we can do that is to take those statistics that we talked about earlier and run them on these plain old everyday JPEG files. And if we do those statistics on enough JPEG files, we should get a really good understanding of what a standard JPEG file looks like. One way to do that is just take a bunch of pictures and do the analysis on them and see if you can figure out anything in common. So we'll take these 4 pictures here, 3 of which are similar and 1 of which is deliberately different, and see what kind of statistics we can get on them. These are the commands to run the basic statistics. Again, all of it's in the README file on the project page. But the basic idea is we're going to have this program freq.py, which is a frequency analyzer, and it's going to help us run these stats automatically, which is frankly the best way to do statistics. Trust me, having tried it both ways, automated is awesome. Also, we can look at the histogram, which is just a picture view of the frequency of the bytes. You know, is byte 47 twice as popular as byte 26, for example? A histogram draws a nice, pretty picture, and we can intuitively get that information fairly quickly. So we look at FunnyCat1, and what we end up figuring out is that there's this mode, byte 0, that seems to show up a lot more than any of the others. In fact, twice as much as any other byte. And we also see some things like that the arithmetic mean is 123 and the median is 123. Those are not too far off of the standard value. So one of the things you would need to do is say, well, what would be a standard value for a JPEG? So JPEG files are binary. They have values ranging from 0 to 255 in some frequency. Byte 0 occurs some number of times, byte 58 occurs some number of times, and so on and so forth. So the closer that the median is to 128, 255 divided by 2, 127.5, but if you round up, about 128 would roughly be the middle, right? So JPEG files actually are 123, so they're not really very even, right? They're actually skewing down away from the median. The standard deviation is kind of the average amount that you deviate from the average. I know it's confusing, it's like an average of average. But the idea being is, on average, how far off is each byte from the median? And this value of 73.96 means that the bytes are all kind of off, but they're all kind of off about the same amount. So we have an entropy of 7.98. And that comes in handy if somebody actually sent a file, like, let's say they not encrypted, let's just say that they sent a text file, a text file that was a book, or an English book. That's going to have an entropy, at least we would expect anyway, of somewhere around like 4.5, 4.6, something like that. The entropy here is 7.98. It probably really is a JPEG. It's probably not a trick. We could also look at the file headers and make sure it starts with the FFFE or whatever the JPEG start symbol is and the end symbol, and do things like that just to make sure we're on the right track. So we do this again for the second picture and get largely the same statistics. Byte 0 is dominating. It's not, on average, perfectly distributed bytes frequency. the third picture ends up being pretty much a duplicate of the first two as far as statistics go. You know, slightly different, but not a whole lot. And then we get to Larry Bird. And Larry Bird has actually got a mode of 32, which is a space character. All the other three had a mode of 0. So that's different. So it is kind of interesting to pull in some pictures that are different just to prove the point that you really want to be as specific as possible. Like if you feel like your adversary is encrypting a map of the battlefield, for example, you probably really want to look at JPEGs that are maps of geographical areas and do your statistics on those and not just pick any random JPEG that you got off of Google Images or whatever. If you think it's satellite imagery that's been encrypted, then grab satellite imagery images and do statistics on those, right? Because you want to try to get the statistics as close to your target as possible. Whatever it is you can learn from that traffic analysis is going to be really helpful. So finally, we get this chart that basically shows that the mean, it turns out, is probably not super interesting, except for the fact that the mean does tell us JPEGs do not have a normal distribution. Great. The mode has predominantly zeros, all except for Larry Bird. That's going to come in super handy. So again, the mode is the popularity contest of statistics. The mode is the most popular character in the file. So what we've established here is that we think that our encrypted file is a picture of a funny cat because the name of the file from our traffic analysis is encryptedfunnycat.jpg. So chances are the mode of the file that we're targeting is probably going to be 0, right? Because all the other cats, when they all have a mode of 0. 0 is by far the most popular character in that file. All right, so now let's look at how does Visionaire, the cipher itself, change the files. So, because in their traffic analysis, we learned that it's an encrypted funny cat, and we also learned that they're using this Visionaire cipher. All right, and just a side note, in the pen test, the way we figured out what the cipher was is on another server, they had actually left a program that did the encryption. They didn't have the key or anything like that, but just the actual program itself, the binary that did the encryption was there. And so we encrypted some files and that we had deliberately filled with like all zeros and stuff like that, you know, files that are good for understanding statistics. And that's how we figured out later that it turned out to be a Visionaire cipher. So here's our strategy for studying this Visionaire cipher now that we've kind of studied these JPEGs in the first round. So we're going to encrypt this file, and we're going to run statistics on the file just like we did on the plain text. We'll compare those stats and see if anything makes sense. These are the commands that I use to encrypt the file. I use the Visionary program to do the file encryption, and then again, we're going to use the frequency analyzer to do the frequency analysis. So same frequency analyzer program, run the exact same way that we did for the other files. So the way the Visionaire file works is that you take this key and you line it up over top of the first X characters of plain text. Now in the example here, the key length is 5, so I've broken up the plain text into 5-byte blocks, okay? And then I shifted the first letter, H, in the word hello, 1 space, the letter E and hello, 2 spaces, and so on. When I got to the O in hello, we're all the way up to shifting 5 spaces, so the O turned into a T. But then I ran out of key, and I had to start the key over again. So when I go to encrypt the word world, the W starts back over with a 1 again, and then goes all the way through 5. And not surprisingly, we can kind of think of this as trying to break 5 individual shift ciphers, right? Like if we think of everything encrypted with the number 1 being a group, and everything encrypted with the number 2 as being a group, and so on and so forth. I'm kind of giving a hint as to where we're going to end up going with breaking the ciphers. Any questions on how the cipher has transformed the word into the ciphertext? All right, so let's compare some of the statistics that we ran on the original files and look at how the cipher changed the file. So the items in blue are the items that are not super interesting. Those are the ones where basically they're the same. So doing differential analysis, they're not interesting statistics. The statistics that are in red were different. And since we're doing a differential analysis here, those are interesting. So now the mode changed from 0 to 216. But you would expect that, right? Because every time there was a 0 in the file, there's some key byte that's shifting that 0 to some other character. Now, we don't know if it's shifting 50 spaces or 2 spaces, because that's determined by the key, right? But we do know that the 0 is getting changed into something else that's not a 0. I suppose unless the key was 256, and then it would take the 0 and flip it all the way back around to the 0. But there's not a very great chance of that happening, about 1 in 256 on average, right? So the mode count, though, is very interesting. Notice how there were 394 zeros in the unencrypted file, but there's only 203 of the 216, the mode of the encrypted file. There's only about half as many of the most popular character. So what's Visionaire doing? It's flattening out the distribution of characters, right? It's taking the spikiest of all characters, and it's spreading that character out over X number of other characters. So if you had to guess, how many other characters do you think that the mode is being spread out over? Does it have anything to do with the length of the key? Remember how the key worked? So it's probably going to be about the length of the key characters that the mode is getting spread out over. In other words, you can think of the key as setting up a series of buckets. And it's shifting the first 0 it comes across, and the second 0, assuming they're consecutive, and splitting those up into little buckets. And that's why the mode is dropping. It's just getting smoothed out over the whole entire ciphertext. The little red arrows indicate that there's a distance between the mode and the anti-mode. So in the unencrypted picture, there was about 400 zeros, and there was about 95 of the least popular character, which was 215. In the encrypted file, there was 203 of the most popular character and 117 of the least popular character. So the mode and the anti-mode are coming together. So not only is Visionaire flattening out the distribution, it's also raising up the least popular characters. It's also putting some other characters into their buckets and smoothing everything out. And in fact, that's what we see in the actual histogram. So if we do clear the screen, if we use the frequency analyzer, so if you need help, you can just do -H. But the idea is going to be to do the CPM, which is count, percent, and histogram. And we're going to do that on the test file. So let's only look at the top 10 because the screen gets a little busy pretty quickly. So -T10. Okay, so look how spiky it is on the unencrypted file. And then we'll change over to the encrypted file. And notice how everything smooths out. That big tail that was there earlier got spread out. Whoops, went too far. It got spread out over the other bytes. So everything got a lot smoother. All right, so now we'll take a look at how can we actually break this cipher. Well, the idea we hinted at earlier, we said that the way the Visionaire was working, the first character, the 6th character, the 11th character, and so on and so on and so on, we're all getting encrypted with the same key. And then the 2nd character and the 7th character and the 12th character, and so on and so on and so on, we're getting encrypted with the same key. Now, of course, the reason that it's in blocks of 5 in this example is because the key length in this particular example happens to be 5 characters. That's where we run out of key and we have to start over. So there's 5 buckets. If we rearrange that ciphertext we just looked at, let's line up the columns. So the hello world turned into ignot x quippy. Okay, so we're going to take the I in ignot and we're going to line it up over top of the x and x quippy, because we know that those two characters were both encrypted with the same key. In this case, we know what the key is. It was the number 1, right? And we know that the next two characters were both encrypted with the number 2, and so on and so forth. And that makes it possible for us to treat these characters as being just a simple little shift cipher. Now, if we knew the mode, the most popular character of the ciphertext column, it might be reasonable to assume that's probably the encrypted version of the mode from the plaintext. 0. It's probably the encrypted version of 0. So now this is turning out to be actually not too difficult. We just need to line up the ciphertext into these columns. But there's a major problem. We don't know how long the key is because we don't know what the password is. So we need to go about figuring out how long the key is. So the plan is going to be to do exactly what we talked about, which is to line everything up into columns and then just figure out what the mode is and just guess that that's probably, most likely, statistically speaking, the character 0 encrypted. And we'll just shift backwards that many bytes and boom, that's the key. But we're going to have to figure out how long the key is to do that. So one of the ways we can do that is through index of coincidence. What we'll do is again, take that entire ciphertext and make a copy of it. Put it underneath of itself. And then we're going to shift it over one spot. And we're going to run the statistics on that spot and figure out, well, what's the chances of getting doubles? And then we'll shift the ciphertext beneath itself 2 spots. And again, figure out what's the chances of getting doubles. 3 spots, 4 spots, 5 spots, 6 spots. And we'll keep going, and we'll keep running these statistics, counting what are the chances of getting doubles every time we shift the ciphertext over one more spot underneath of itself. So there's a fellow named Friedman who came up with this idea originally, and he, not surprisingly, was trying to break the Visionaire cipher. At this time, the Visionaire cipher had been a military-grade cipher for almost 300 years. So this thing had been proven itself really well for a long time. Again, this predates the time of computers. And so the cipher did really well against manual analysis until this fellow came along. And so he came up with this counting formula here, which just, what it does is it just counts the occurrences of doubles and then divides by the number of chances that there were to have doubles. In other words, the number of letters that were compared. So here's an analogy. This is not the index of coincidence, but this is an analogy. Imagine I took the letters of the alphabet, 26 of them, and I put them into a bag, and I said, pick a letter. The chances of you getting any particular letter in that case is about 1 in 26. We put the letter back in the bag, shake it up again. I say, pick another letter. The chances of you getting any particular letter, 1 in 26. So the chances of you picking the same letter 2 times in a row, assuming the contest is fair, is 1 in 26 times 1 in 26. And that's where you get the 1 over 676. Now, let's think about if you did the encryption. If you do the encryption and the key length is 10, the chances of you getting any particular key byte is 1 in 10. Plus, you've also got to pick the same letter. So what are the chances of actually getting the same letter if you encrypt it out of the bag 2 times and you don't know which key byte was used to encrypt the letter? It's 1 of 10 possibilities. Well, the chances are even 10 times worse, right? So now you've got, only a 0.015% chance. However, if we align those columns just perfect, in our example, if we align the columns at a 5 spot, shifting at 5 spaces, 10 spaces, 15 spaces, whatever, as long as it's divisible by 5. The key is taken out of the picture. It's the same key. It encrypted both letters. So the chances of you getting the same letter twice go back to being 1 in 676. Yeah, I know, it's not great odds. It's 10 times better, though, than if you use the encryption. So I think we're on to something here. Now, in real life, index coincidence does not work that way. I was just drawing an analogy. Letters are not 1 in 26 chance. The letter E is much more likely than the letter Z. The letter T and the letter A are much more likely than the letter O and P. Okay? And this table actually shows the frequencies of the letters. And this is the formula for the probability of actually getting a particular key byte. Because what we didn't take into account before is there's more than one way to get the same ciphertext. After all, the letter E shifted once as F, but so is the letter D shifted twice, and the letter C shifted 3 times. So there's actually a lot of different ways to end up getting the same ciphertext. But the odds are still going to be in our favor. So let's say that you take these frequencies of these English letters, okay, and let's presume that it's plain text. And you multiply up all those frequencies. So you got to take the chance of getting a letter A in the first place times the number of A's that are actually in the batch, and then the chance of getting a letter B times the number of B's, and so on and so forth. And what you'll end up finding is that when you multiply all that out, it comes out to be 0.065. So remember 0.065. Now, if you go back to our random chance example, in other words, remember how Visionaire had a tendency to kind of smooth everything out? The mode got spread out. So in English, the mode is the letter E, usually, right? I mean, typically it occurs about 12.5% of the time, and the next best letter is T, around 10%. So the Visionaire, though, smoothed out all those bumps in the road, right? So if you take something and it's perfectly encrypted, we'll just go back to assuming you've got exactly a 1 in 26 chance of pulling that ciphertext out of the bag. And so you take 1 in 26 times 1 in 26 and do that 26 times for 26 letters, and you end up getting 0.038. Now, 0.065 is not super different from 0.038, like our 1 over 6,700 was different than our 1 over 676, but it's still about twice as good. So we can still use the index of coincidence. And here's an example. I just threw a very small alphabet up onto the screen and did some random sampling. And in my little alphabet here, there's only 3 letters, A, B, and C. Very trivial example. And in the first instance, there's 2 doubles. There's the letter A and the letter C. The second instance has 3 doubles, and the third instance has 1 double. Now, it's the exact same ciphertext. It's just shifted over 1 spot, 2 spots, and 3 spots. So in the first instance, the 2 doubles, we had a 0.6. The middle is 1.0, and the end is 0.375. So if you had to guess, what would you assume the length of the key was in this particular case? And this is all you know. Does it make sense that it would be the middle one because you had the most occurrences of doubles? So statistically, there's this better chance of getting 2 letters, 2 ciphertext letters, to turn out to be exactly the same. Fortunately, the Python program, the freak.py, can do this for us, so we don't have to sit here and count the number of doubles in this huge ciphertext that's got something like 1 million characters in it. And so let's take a look at the encrypted file. So we're going to bring up that program again, and I'm going to change it to doing the IOC, or index of coincidence. All right, and it runs for 49 shifts, okay? So check out the histogram. When we get to 8 shifts and 16 shifts and 24 shifts, while it's not 10 times as likely that we're going to have that character end up being doubles, it does seem to be a lot more likely, doesn't it? And it can't be a coincidence that it happens on the 8s, 8, 16, 24, 32, and so on. Chances are that key is 8 characters long. So now that we know that the key is probably 8 characters long, we can go back to the ciphertext, the first couple of rows of which is shown up here on the slide, and we can break it up into blocks of 8. And we're going to take those blocks of 8 and line them up underneath one another. We're going to end up with very tall columns. The first column all encrypted with the same key of the password. The second column all encrypted with the same key of the password, and so on and so forth. So all we need to do now is solve 8 shift cipher problems, put it all together, and we should be able to recover the password. So the way that we're going to do that is we're going to assume that the mode of the column of ciphertext is the number 0 encrypted, because byte 0 was the mode of the plaintext in cat pictures that were encrypted, right? So let's just say, for example, like we can see on screen here, byte 17 happens to be the mode of the very first column. Let's assume that byte 17 is 0 encrypted. That means that the key used to encrypt the 0 must have been 17 because it was shifted 17 spaces. The second column mode is actually only 14. So chances are byte 14 is the key because 14 minus 0 is 14, and so on and so forth. And we'll do that for all 8 columns and see what we end up getting. All right, so from our previous example, I'm going to change T to 1. I'm only interested in the most popular byte. I don't really need to look at the top 10 bytes anymore. I'm going to add the G for guess, and I'm going to add the COL or columns, and I'm going to put in 8. And I have to put in 8 because the IOC exercise told us that the password was 8 characters long. All right, and let's look at the results. Oops. Let's start with the first column. Okay, so byte 17 is the mode. R is the 17th character in the ASCII character range if you start from counting from the letter A anyway. Okay, and uppercase R, of course, is the 17th character if you start counting from the capital letter A. And number-wise, that's the letter A if you start counting from the number 0. Do we know which one is the right letter? No. We just have a really strong suspicion it's probably the letter R. Is it a capital R or a small r? I don't know. But it's probably the letter R. The second letter is probably the letter O. Is it capital or small? I don't really know. It could be a greater than symbol, but probably not, right? We're talking about humans here, okay? So the third letter is probably C. The fourth letter is probably K. The fifth letter is probably Y. And then the last 3 letters are probably 329. So now we've actually reduced the size of this problem quite a bit. The next thing we need to do is we need to iterate through the possibilities of the upper cases and the lower cases. And there's some Perl scripts in Kali that can do that for you pretty easily. Or even some that I think come with John the Ripper that can do all these iterations for you. And then we can try those, 200, 300, 400 passwords on the file and see which one works. But you know what? Do you really need to try every possibility? Maybe. Chances are, though, if a person picked this password, it's probably capital ROCKY329 or just ROCKY329, right? So just give those 2 a shot. And as it turns out, the password really is ROCKY329. So we were able to end up figuring out what the password was. So here we see the ROCK starting to show up because we're going to figure out what the mode is and then shift down that many bytes. And this is the Python that we just ran to do that analysis. And we ended up getting back the password Rocky329. Not case sensitive at all, as it turns out, in this particular exercise. The password that they used in the real life file was 32 characters long, and it didn't matter because the length of the password doesn't make the problem any more difficult. The IOC told us in one command that the password was 8 characters long. We didn't have to run 8 commands or 32 commands, right? One command. The problem really is linear, and that's why the Visionaire cipher falls somewhat relatively easily because it is doing a linear shift on the characters. It's a complicated shift, kind of like the affine cipher is a little more complicated than the shift cipher, but it is linear, so we can get it in linear time. So how can we make this better? Well, you know what? If we actually wanted to just work on JPEGs, this is pretty good the way it is. But what if we wanted to work on other kinds of files, PNGs or text, emails, things like that? And what we would need to do probably is add what's called curve fitting techniques. The idea being, if I want to make sure that I've decrypted something that's English, and I want to test and see if it actually kind of looks like English, the E ought to show up 12.5% of the time. The T ought to show up about 10%, and the A about 9%, and so on and so forth, right? Imagine that being a curve. So if we do a frequency analysis on some stuff that we've decrypted with capital ROCKY329, which is the wrong password, the curve wouldn't fit. But if we use the right password, ROCKY329, the curve should fit pretty well. So curve fitting techniques will definitely improve freak.py. And there's some other tricks we would need to do if we found out that our adversary was encrypting, like I said, different kinds of files, PNGs or GIFs or whatever file type it was, like a spreadsheet. All right, so any questions? Any questions at all about cryptography or just pen testing in general? Or fun little problems like this? All right, I'll throw some references up here as well. And the book that I used to figure out the math in this exercise is the number 6 there, the Cryptography Theory and Practice. So to give credit to that fella Stinson for helping me out. And a really good book for just kind of learning about cryptographic algorithms just kind of in general is this one here. Oh, sorry, I didn't put it in here. It's by Parr, P-A-A-R. I apologize for not putting it on the slide. Christoph Parr. I guess that's how you say it. I really liked his book. It was really easy to read and really easy to understand for somebody who's not a math major like me. So that's also a really good one. All right, I'll leave my contact information up here for a few minutes, and thanks very much for having me today.